In this video, we're going to talk about the creation of 6-bar mechanisms, and each team member will create a separate inversion for one of these 6 bars and create, the parts from scratch, and then a bill of material, exploded assembly view with a bill of material and balloons, trail lines, and so on. And one of the reasons we're doing this is because for the project, you will be creating a SOLIDWORKS model of the 4-bar lifting mechanism, and you'll basically have to do these same types of things for the project. So we're going to be looking at the 2 types of 6 bars, the Stevenson 6 bar and the Watt 6 bar as shown here. And note that for the Stevenson 6 bars, there are 3 different inversions, 3 possible inversions, and that the Stevenson 6 bar you can actually see is made up of, if you disconnected these, you would have a 4 bar, right? Ground, 1, 2, 3. And then on the other side, if you disconnected these 2 joints, you would have a 5 bar, 1, 2, 3, 4, 5. And you can look at any of these 3, and that they're made up really of a 4 bar and a 5 bar. And whereas for the Watts 6 bars, they're all 4 bars, or a combination of 4 bars, right? 1, 1, 2, 3, 4, ground 1, 2, 3, 4. Same thing with this one. So you have to ensure that at least one of the links in these 6 bars can go through a 360-degree revolution. So if we look at this one right here, so this one again, you would have ground 2, 3, 4. So there's the 4, and then 1, 2, 3, 4, 5 that way. So if you look at these lengths right here, and for this particular case, these are 4 inches long. The distance from here to here is 3.2. That's a 1 inch. And the distance between these 2 joints is 4 inches. So these distances are 3.2, 3.2. This is 1 inch, and that's 4 inches. So if we apply the Grashof equation, then we find that it is in fact Grashof, right? In other words, the sum of the shortest and the longest. So in this case, 1 plus 4 is 5. These are each 3.2, so that's 6.4. So the shortest and the longest is less than the length of the other 2 links. So we know that this is going to this link right here will be able to do a complete revolution. And as long as these other 2 links up here are long enough, now it could be possible that they're not long enough for this one to do a complete revolution. So in other words, if we look at where are they closest together. So suppose these 2 links were much shorter, and maybe they just had a slight angle here. So now when we try to do the complete revolution, at this point, you can't get to this point because these 2 links are too short. But as long as these are long enough, for when these 2 joints here are the furthest apart, and these other 4 joints right here make up a Grashof 4 bar, then we know we can do the complete revolution. Okay, so what about the other type? So this is the other type where now we actually have 2 4 bars, right? 1, 2, 3, 4, or ground 2, 3, 4. So if this one is Grashof, and as long as these are long enough, then you can see that you can get a complete revolution here. But does this 4 bar have to be Grashof? So that's a question we'll have to pick up with the next video. So for this particular inversion, we know that we can get this link to do a complete revolution. We know that this distance right here is 4, this is 3.2, that's 1. So 1 plus 4 is 5, that's less than 6.4. The sum of these 2, this is a Grashof. What about this one up here? Well, in this particular case, this is 3.2, this is 3.2, and both of these are 4. So this is actually a class 3, right? The sum of the longest plus the shortest in this case 4 plus 3.2, is the same as the sum of the other two, because the other two are 4 and 3.2. So that one actually is Grashof. What about if we have a case where the other 4-bar, we have one 4-bar down here that's Grashof and the other one isn't? Will that work? So let's look at that case. Okay, so here, these distances are the same as before. This is Grashof. And now we have 3.2, 3.2, 6, and 4. Well, so the shortest is 3.2, the longest is 6. That's bigger than 4 and 3.2. So this 4-bar up here is not Grashof, but you can see that as long as those links can reach, it doesn't matter that they're not Grashof. So in other words, when these are as close as they get together, suppose these were shorter so that, again, maybe you had a slight angle here, but when you try to rotate this, they can't get, that far apart. So again, as long as you have one of those 4-bars as Grashof and the other side doesn't have to be Grashof, as long as they're long enough to reach the positions they need to get to, you can still have a complete revolution of one of the links. And for the lab, for the SOLIDWORKS assembly that you're going to create, you have to have at least one link that can do a full revolution, regardless of which inversion you pick. Okay, so once each team member has the an e-drawing of their exploded assembly, and you've gotten the check off from the SA or TA that you have at least one link that can rotate 360 degrees, and then you'll want to submit all the e-drawings into the e-drawing Dropbox for this lab. And the trick, though, is that with Canvas, if one team member uploads their e-drawing into the Dropbox, and then another team member uploads theirs, it overwrites. So what you have to do is just have a single team member have all the e-drawing files and submit all the files all in one shot to the Dropbox. So sorry, that's an issue with Canvas. But anyways, hope you have fun doing this.